Ninth lecture of CS224D. Today we'll talk about recursive neural networks. I have a somewhat personal relationship with these since I worked a lot with these kinds of models during my PhD. So we'll actually spend 2 lectures on these. Just like recurrent neural networks, they're pretty important. They're very flexible kinds of models. And so basically today we'll motivate them a little bit with so-called compositionality, meaning sort of technique to get to the meaning of longer phrases. And then we'll actually look at a slightly different kind of objective function, a structure prediction kind of objective function today. And backpropagation through structure is really going to be very similar to backpropagation, which you already know, with just 3 slight modifications. And then the nice thing is that these models are very general, and so if we have enough time at the end, we can also actually have 2 or 3 slides on a computer vision example. Turns out the exact same model will work for images as well. And then in the next lecture we can go and look into a couple of modifications, a couple of extensions to the standard recursive neural networks. When I mention RNN today, it will be mostly recursive neural networks. It's unfortunate because RNNs in the last couple of lectures were recurrent neural networks, and we'll actually look into the difference between those 2 as well. All right, so we're very familiar by now with word vector space models, where words that are similar in meaning and have similar kinds of part of speech tags are close by. So all the nouns are clustered together, and inside the noun cluster would have different semantic substructures. So the vector of Germany would be closer to the vector of France, for instance, and Monday and Tuesday would be closer to one another. But of course, words never appear in isolation. And so far, we haven't really thought about what happens to vector representations when we want to represent specific short subphrases. So what if I have the 2 phrases, the country of my birth and the place where I was born, for instance? If I was to build a text summarization system, clearly I wouldn't want to have both of these together, despite country and place not being that similar, and birth as a noun and where I was born as a verb. But ideally, if we were to build a text summarization system, we wouldn't include both of these phrases, right? And so the question is, how should we represent the meaning of these longer phrases? And the answer that is similar, or the answer we'll basically give to that today is by mapping those phrases into the exact same vector space where we had words. And so just to give you a sort of broader sense of where that puts us, there are a lot of these representations for single word vectors. We look through word2vec and glove vectors. Basically, they're sort of distributed and distributional techniques. There are actually a lot of other ones, such as Brown clusters, which we're not going to cover much in this class. But basically, they also capture co-occurrence statistics. And so they are great, but they really can't capture longer phrases. And then there are a lot of other models that are very widely used, such as bag of words models or the PCA-based models that we discovered for document representations. And those are reasonably good for information retrieval. We just want to find specific documents that mention specific phrases. Or document exploration, we just want to know these documents roughly about politics or sports or things like that. But of course they ignore the word order, and so we can't really get to a detailed understanding inside our representation. And so today we'll look at another technique for finding vectors that really represent phrases and sentences without ignoring word order, and actually trying to capture both the syntactic structure as well as the semantic information of those phrases. So that leads us to the question of how we should go about doing this. And in this lecture, we'll introduce and use the principle of compositionality, which in our case states that the meaning vector of a sentence is determined by the meaning of its words, the word vectors. And throughout the lecture, I will describe those, I illustrate those in 2 dimensions, but of course, they will generally be 25 to 300 dimensional, so much larger dimensional. And 2, the rules that are used to combine them. And unlike before, where we just go from left to right and we just compute 1 vector for everything that we've read so far from the left side, this time we'll actually adhere to the grammatical structure of the sentence, and we'll try to find specific noun phrases that go together. So for instance, my birth is by itself a reasonably grammatical or syntactic phrase. And similarly, the country is a noun phrase, and so we can combine those two. And then of my birth is actually a prepositional phrase. So those, the word vector of of will be combined with the word vector of my birth, and so on. And then ideally, at the end of it, the final resulting vector will actually be somewhere close to other countries in the single word vector space. And so the neat thing about these models today is that they basically can jointly learn these so-called parse trees and compositional vector representations that ideally capture syntactic and semantic information of the phrases underneath them and not of the entire context that we've had so far to the left. So what is sentence parsing? When we say we want to parse a sentence, what do we actually want out of it? So let's assume we start with a sentence like the cat sat on the mat, very simple phrase. What we would want is to have a model that understands that the cat is a proper noun phrase. And I could now replace that noun phrase with any other noun phrase and it would still be a grammatical English sentence. So I could say the car sat on the mat, or the whole class sat on the mat. Like any kind of noun phrase could now be replaced with this one and it would still be a grammatical sentence. Similarly, the mat is a noun phrase, and now on the mat is a prepositional phrase. And again, we could replace that prepositional phrase with any other one and still get a syntactically or grammatically plausible English sentence. So we could say the cat sat, beyond the scope of this lecture. That doesn't make any semantic sense, but is actually a grammatically correct sentence. Right? And that is a big and important distinction, right? Grammar doesn't tell you that much about semantics. And then to sit on the mat is a verb phrase, and together this whole thing is a sentence. That is sort of the standard way of defining the parsing task. We get these discrete tree structures. And they're different depending on the input. Of course, what we will want is not just having these discrete structures, but ideally we want to have, again, everything represented as a vector. And so we'll actually look into how we can compute these vector representations that now represent any specific subphrase without the context. And so the first question we have to ask ourselves here is, do we really need these structures? We're saying we learn structure and representation, but really in the last couple of lectures, we've also learned some kind of structure and representation. It just happened to be that that representation was always everything to the left of what the current word is. And so that leads us to 3 slides of a side note of, should we use these recursive structures, the tree structures, or just chain structures? And this could be a very lengthy argument. I'm going to try to distill it in just three slides. But basically, the main difference here is that chains are actually special types of trees, right? They just happen to always branch in one direction. Right? So from general graph theory, that chains are just special types of trees. And so in that sense, the recursive ones are just generalizations of recurrent ones. And the default could be to just say, well, I just take all the words, and instead of looking at their grammar, I just combine them one at a time. Right? And so you can see this as, when you have these specific words, you could just say, I keep combining them one word to the right, and that is also a tree. It just happens to be able to flatten it out and call it a chain. Right? So in that sense, they're actually not that different. However, the question is sort of then, is language a recursive kind of thing? And so there's a long history here of papers, and I don't think it's yet clear whether this is cognitively plausible. Like, do people really put together specific phrases in their brains and so on? And fortunately, we're not cognitive science class right now, so we can kind of put that on the table and say, well, maybe, maybe not, but recursion is clearly helpful in describing natural language. It is very helpful to say, for instance, that the church which has nice windows, the church which has nice windows is a noun phrase. I can replace that noun phrase with another noun phrase, still got a grammatical sentence. And yet inside that noun phrase, we have a relative clause, which has nice windows, and that itself also contains a noun phrase, namely the nice windows. And so that, from just describing language is clearly very useful. And now there are basically 4 arguments of that we use for now, and to basically say it is just kind of helpful for a lot of different tasks that we encounter in natural language processing. One of those is disambiguation. So here I show you the first 2 parse trees that look a little more realistic, something you would actually see when you parse a sentence. And you see here the sentence, you read them from the left to right. So here, he eats spaghetti with a spoon. And the other sentence is, he eats spaghetti with meat. Now, what this tells us here is basically we have he, which is a personal pronoun, and personal pronouns are noun phrases. So far, so good. We have verb phrases here, and now the entirety of that sentence, eat spaghetti, or that phrase, eat spaghetti with a spoon, is a verb phrase. Eats is the verb. Now, spaghetti is a plural noun. And now this is the interesting part here. This is a so-called PP, or prepositional phrase. And this overall problem here is a PP attachment ambiguity. So if a computer was to read this sentence, and he reads, he eats spaghetti with a spoon versus he eats spaghetti with meat. Now, how can we know whether the computer understands that when I say with a spoon, I actually mean that I modify the way I eat the spaghetti, as in this PP should attach to the verb phrase, versus I say he eats spaghetti with meat, whereas this with, which also just has some noun phrase inside of it, this PP actually attaches to the type of spaghetti because we're not modifying how we eat, we're modifying what we eat. Right? So if we have this kind of structure and we make this explicit, it will be useful to disambiguate these 2 cases, and now the model could actually tell us whether it got it right. And we can do downstream tasks now and also query, for instance, the model and ask, give me all the different ways somebody could eat spaghetti. Right? Maybe you eat it with a fork, maybe you eat it with a fork and a spoon, and so on. Are there any questions about this part? Again, so back in undergrad, I actually took 2 entire semesters of just syntax and grammar theory and things like that. And so, again, this is like an insane oversimplification here. Could literally spend an entire year just talking about all the subtleties of how these trees are created. So it's a bit of a cognitive overload in some ways.
That recursive structure is really good for understanding semantics or grammars, which seems like grammars more look like recursive, but it seems like a little contradictory what you said, because grammar is not actually related to understanding something in the sentences. So I just wonder that recursive structure is really good for your understanding, or just understanding the sentences in a correct form.
So the question is, are they really useful for sort of semantic understanding versus just grammatical understanding? And the answer here is, in some ways, both. And a lot of linguists postulate that in order to understand a sentence, you first understand the words, then you understand how words are put together, and then you get to the actual meaning of that sentence. And you get to the meaning through the structure first. And some people say, well, maybe not, right? So this is very much up for debate. Clearly here we see, a noun phrase. Well, there's no noun phrase here inside another noun phrase, but here that is the case, right? With meat, the meat is a noun phrase, and the spaghetti. So we did understand more about grammatical structure here. And certainly if we were to, for instance, train whether students are using correct grammar, this seems like clearly a very useful model. However, we also got some better understanding of what the model actually understood here when it read those sentences, right? So eating spaghetti with a spoon, and now here the model understood that with the spoon, or understood in quotation marks, understood that with the spoon here actually attaches to the verb phrase and hence modifies how you eat the spaghetti. So we did gain both syntactic and semantic understanding of the sentence. Yes? So I did not. What is the difference between what?
So what is the difference between jointly learning those 2 structures versus individually learning them and then putting them together?
That's a great question. We'll actually get to that a little bit throughout the lecture. So the next three reasons are sort of, let's say recursive structure, cognitively questionable, but clearly useful as a way to describe language. Now, it's also useful for just real tasks. So let's say we wanted to, for instance, do a somewhat complex co-reference analysis, where in co-ref, what we basically want to understand is when you refer to they or it, what did you actually mean when you say that, right? And it usually means you have some anaphora, for instance. So here's an example. John and Jane went to a big festival. They enjoyed the trip and the music there. Now, co-reference resolution would be the task of understanding who is they when I actually mention that, this they right here. And in this case here, it would be John and Jane. So now we want to refer to that entire phrase. Now, when I say they enjoyed the trip, and I ask, what do you mean by the trip? Then ideally you would say, well, the trip meant they went to a festival, right? And so now going to a festival is a specific type of trip. And it's not that Jane and John went to the big festival is the specific type of trip. It's just, going to a festival. So you might want to refer to just that. And now somebody else could have that same trip, and you can refer to that as one coherent unit. And now there would be potentially, the big festival. Maybe there are two festivals, a big one and a small one. They went to one, not the other. Now you go basically there. So this here basically we've seen a couple of times. We could also refer to just her and just him, for instance, just Jane and just John. And in both cases, we wouldn't want to have only a representation for everything that was read until now, right? We would only want to have something we can refer to that is a sub-phrase in that sentence. Third reason is that the labeling sometimes becomes less clear. So if we basically only have a single label at each word. So here we have a sentence such as, I like the bright screen, but not the buggy slow keyboard of the phone. Now, ideally, we could just classify buggy slow keyboard of the phone, or buggy slow keyboard by itself, as an entity, and that is negative, whereas something before here is positive, right? And we don't necessarily just want to classify the entire sentence here or this entire paragraph, but we'd ideally understand, each of these sub-phrases, and they can have different kinds of labels if we were to classify sentiment, for instance. And again, here, it is an interesting co-reference problem. It was a pain to type with, or it was nice to look at, depending on what the information here is, the semantics of what's following the it's actually either referring to the screen or the keyboard. So this is the task of co-reference resolution. It's actually kind of an interesting task in NLP. All right, and then the last argument is somewhat of a pragmatic argument, which is in some tasks it just works better to use these grammatical structures. But this is also an ongoing field of research. So maybe eventually we'll find that we could get away with just some very, very deep LSTM model, and we don't need them at all. And maybe whenever you have a phrase, you can kind of have some neurons that kind of just capture now as a phrase, and then the forget gate turns on, and the next layer will kind of deal with this thing. It's still up for debate. It's a very active area of research. But OK, let's for now assume, and it's still the case, that on some tasks, these models work the best right now on some standard benchmark data sets. And so let's define actually what a recursive neural network is and how we get these parse tree structures. So basically, we'll have two inputs, which are, in general, the candidate children's representations. So in the beginning, those will just be the words, for instance, the and mat. And then later on, it could be representations or phrase vectors that actually already were computed before. And the output in the first kind of example, where we actually look at how to compute the tree structure, will be two things. The first one is the semantic representation if we merge these two nodes. And the second one will be a score of how plausible the new node would be. So ideally here, again, we'll compute a score that will say this is a reasonable syntactic phrase. And we want to increase that score if it is actually true, and we want to decrease it if it's some random ungrammatical phrase. So what are the equations for this model here? Well, it's a very simple one. The first thing we do here is we just concatenate C1 and C2, the children, the left child and the right child of each node in the tree. We concatenate them, and then we multiply them by this matrix W here. And now the parent vector P should have the same dimensionality as each of the single children. So let me ask you, what should the dimensionality now of W be? Let's say C1 and C2, each one is n-dimensional. It's an n-dimensional vector. Now what should the dimensionality of W be? Say louder. Yes?
N by 2n.
Exactly, n by 2n. And so to understand this a little bit, we can also write this in a different way. We could, instead of writing W times C1 and C2, we could rewrite this and say, well, W is a block, W1, W2. So like we said, this is an Rn by 2n matrix. And this matrix will be exactly this. And we have here C1 and C2 as our vector representation. And now this is actually equal to W1 C1 plus W2 C2. Right? And that looks very similar to various equations we've had in recurrent neural networks too, where one was the history of, that we had in the past, ht minus 1, and the other one is x1, the next word. Now it just turns out that C could be both. It could be single words, or it could be hidden dimensions. And we'll go through an example here in the next couple of slides. So the reason we call this recursive and before recurrent is that we use also here the same W parameters at all the nodes of the tree. So in order to compute any one of these here, we'll share the weights, or we tie the weights, and basically have the same W here to compute every single parent vector. Yes?
So this isn't order agnostic, right? It requires the probabilities and your W's will encode the belief set words come in a linear order, right?
That is correct, yeah. This model is not, it really depends on the order of the words. Okay, so this is the main equation. And again, we see here, this is really essentially just a standard single layer neural network. Just happens to have as input two vectors that we concatenate, which the model doesn't really know. So the model is just a single vector. But the way we put them together is by taking one vector from the left child and one vector from the right child. So this is the central equation of today. And so now, how do we actually use this to compute a tree structure that is, captures the grammar of that sentence? We basically, and this is the first simple version of how to describe this, and basically the only one we'll describe in detail today, so-called greedy search mechanism here. We just basically look at how likely would it be to combine the vector of and the vector of cat with this neural network. And that would get some kind of vector representation first, and then a score that was just a linear layer. So again, here the score, which we kind of skipped, is just a simple inner product, same kind of score that we used before. So now we look at this, and then we'll just look at every possible pair of words and how likely they would be to combine to a reasonable syntactic phrase. And now it's just, in grammatic structure and according to linguists, on the is not a reasonable syntactic phrase. But the mat is a nice proper noun phrase, so that would get a large score. And likewise, the cat is a very obvious, very simple combination of a determiner and a noun, so we put those together. So now the cat here gets the highest score, and in this kind of greedy search mechanism, we'll just say, all right, well then let's combine those two. Let's, instead of having these two separate word vectors here, we'll now just take the phrase vector, which is really just the output of the hidden layer. So now the model basically has one vector here, and that's the first vector of the sequence, and that vector represents now the cat. And now we basically have here the cat as a vector, and then still a set on the mat as each one being a separate word vector. And now the model doesn't yet know how likely would it be to combine the cat sat. And so this is where the recursion comes in. The output of the first time we applied the neural network becomes the input to that same neural network, and that's why it's recursive. So now the cat sat is somewhat of a reasonable phrase. We could just say the cat sits instead of the cat stands. And so this would get a reasonably large score. However, the mat was an even more obvious noun phrase, and so we'll merge those two nodes next. And now again, the model doesn't know how likely it would be to combine the word vector on with the phrase vector the mat. And so we'll again apply the same neural network. Yes?
Could you maybe talk about a little bit about how, if at all, this is different from like CYK parsing?
That's a great question. Well, actually, it goes a little bit too far, so I can't go into too many details. But for those of you who actually have taken the 224 and know CKY or CYK, it's just three names. Parsing and chart parsing. In chart parsing, you can actually make certain independence assumptions, kind of like you make Markov assumptions for language models, where you say, I don't care about anything else that came before, but right now, this phrase is a noun phrase. And because of that, you can then say, well, I can find the global optimum here, because I can make certain simplifying assumptions, use dynamic programming. Here, you can't really use that because the vectors on which you make those assumptions are continuous. And so really changing the vector just a little bit would change potentially the overall score. So while one phrase might be locally the best, highest scoring phrase, it might not actually lead you to the global optimum. So all you could do here is so-called dynamic beam search. But don't worry if you weren't able to follow that little side note. So in the end, what we'll do is a CKY-like beam search. But again, don't worry about this. It's enough to understand sort of this greedy procedure here for finding the best tree. OK, so now we basically keep building up this tree, find the highest scoring potential candidate, and in the end, have the full tree structure. Yes? Sorry, can you speak a little louder?
I was wondering whether there's some sort of constraint and symmetry between the first part of the level and the second part.
So are there certain constraints on these two that they have to be symmetric? That's actually an interesting question. There are none. So right now, they can just be any arbitrary matrix. And it turns out that there are interesting extensions that we'll go into later in the lecture that actually allow us to really understand a little bit better how what the role of these two blocks are, the left block and the right block. We'll get to it in a couple of slides. Yeah. But yeah, in general, it's just a W matrix. It'll be updated with SGD or other kinds of optimization methods, and there's no way to sort of enforce kind of symmetry. And you don't want to enforce symmetry because maybe on the left phrase or left word might be more important than the right one. Are there any other questions on how this sort of greedy search procedure happened?
Are we going to have the same neural network class after training?
Yeah. So yes, the same neural network here was used for every single node computation.
So to me, that neural network class is sort of a combined two-word back to a word to back to another vector representation in the same space, right? So sort of a different location between these two words to back, and then in the end, that kind of sentence, the cat set and the map is projected in another location in the same word to back space. And then I just wonder if it's okay in terms of the result, and also wonder, for example, you found another location of that sentence on the word to back space. Is it really close to some of that word in that sentence?
Right, so the question, I guess, is it's a little fuzzy. Is it okay to do this? Well, it turns out it's okay for tasks, for certain tasks. It's good enough to get the state-of-the-art performance on them.
Is it better to have a different kind of neural network class, a different level or something like that?
Yeah, so the question is it good to have different kinds of neural networks and actually relax the assumptions? So the way I described this so far is that these kinds of models are actually more recursive than actual natural language. Natural language has sometimes a noun phrase inside a relative clause inside a noun phrase. Here, we use the exact same neural network at every single node of the tree. And so we'll actually relax that assumption later on in the lecture. So how do we actually train this? We will use a similar max margin objective function to what we had used before in one of the earlier lectures, but now we'll define the score of the entire tree. And we don't just have a single window, we have a tree that actually was computed from multiple different kinds of scores. And so the score of the full tree is, for us right now, simply the sum of all the scores at each node. So let's define here the score of a specific sentence X with a specific tree Y. We basically look at all the nodes that that tree had, and we compute the scores at each of these nodes. And again, these scores here were just simple inner products with the same U vector. So here comes the most important and kind of interesting new equation of today's lecture. Basically, this is called max margin parsing, and we have here this max margin objective function. So let's walk through this objective function very slowly. What we want to do, we want to generally maximize this function, and we assume we have a labeled training data set. So we assume a bunch of linguists sat down and said, for every sentence xi, I give you the correct tree yi. And now this again here was just a sum of all the nodes of those trees, and that sum was just a sum of a bunch of inner products, right? So again, when you think about, how would you train this model, it's just a bunch of gradients of, a sum of inner products underneath which you have a neural network. Okay, so that's easy, but now if we just maximize all the scores of all the correct trees, well, we could just, everything would go to infinity, right? We'd just maximize everything. What we actually have to tell the model is how to deal with finding the right tree by itself. And this is what the second part here is. So we're going to try to find the maximum over this set. And the set A of xi is the set of all possible trees that you could construct from xi. And so there, if you're familiar with combinatorics, there are Catalan many potential binary trees. So it's exponentially many possible binary trees. You can actually compute that number, and it blows up very, very quickly. It's an exponentially many number of trees. So this is where we will have to find some smarter way to go through them and find the highest scoring one. And the simplest one that I described was in basically this greedy procedure here. We just take the highest scoring current step and hope that that will lead us eventually to the highest scoring tree. But of course, that isn't necessarily true. Here we found the correct tree, but maybe the model incorrectly would have said cat sat is the highest scoring one, and then we couldn't recover that later on, right? So this is basically a search procedure, and there are different ways to do search. And in some ways, if you're interested in kind of the search aspect of machine learning and AI, then I think 221 is the right kind of lecture to take, sort of an introduction to AI. Different kind of search strategies. All right, so let's assume for now that we find the highest scoring one simply with this greedy procedure, and we basically, do exactly what I described the previous slides, and now we define one specific y that is the maximum of all the trees we could build. And now, because of this minus here, we're going to try to minimize the score of that highest scoring tree. And let's ignore this part for now. If the highest scoring tree that we're now minimizing actually happens to be the exact correct tree, well, then we're done here, right? Then yi and this y are actually the same. These two cancel out, and we're done. And now this is where the interesting margin penalty comes in, which is indeed actually an important part of this objective function. And this margin here essentially penalizes every incorrect decision that you have made. So if you incorrectly combine two words, then you add a 1 to that tree structure. And the result of that will be that once you actually get the correct tree here as y, and y actually is yi, then that y will have a score that is higher up to a certain margin to the next scoring but incorrect tree. Let's parse that. Pretty complex sentence. So essentially what this delta here does is it encourages the model to make mistakes. It will add a bonus point to every mistake the model makes, and once it goes past that bonus, it actually makes the right decision with a margin of delta, which you usually just for every incorrect decision we set it to 1. So the score for the right decision will then be 1 larger than the score of an incorrect decision. So in the beginning here, we encourage the model to basically do the worst possible thing, right? And then the model makes all these mistakes, and then you can tell them, well, these were all wrong, and you minimize all the scores of these incorrect decisions. And that's where, yeah, that's sort of the idea of the max margin loss. Are there any questions about this? Yes.
Does the loss function, so I imagine there's some sort of representation going on.
Yeah, so in almost every single weight in all these different loss functions that I always describe has a standard L2 penalty on all the weights.
Okay, so does that mean that the loss function doesn't have any parameters, it's just one adds one, or sorry, this delta function?
The delta, yeah, the delta does not. It just basically encourages the model to make mistakes during the search procedure. It doesn't actually backprop something in itself. Yeah, great question. Yes?
Can you just describe the notation a bit more clearly, like what are xi's, yi's, and
Okay, so again, xi is the sentence. So in this case, your cat sat on the mat. Yi is the correct tree structure. Basically, linguists sat down, went through a lot of sentences. In most cases, it's so-called Penn tree bank. And in the Penn tree bank, they said, all right, for this sentence, this is the correct grammatical analysis of that sentence. All right. Yes?
So can one term of J be negative?
Can one term be negative?
Yeah.
Yes. So these scores here are just inner products, right? Inner products with real numbers. So they can be very negative. All right. So how do we actually train this kind of model, and what does this look like? Again, in some ways, you could just do this right away. It will require a lot of thought. Little embarrassing, but I actually had reinvented this whole thing. I didn't know it existed. I didn't have a name for what I was doing. So I actually had reinvented this whole thing, and only later I was like, oh, I'm going to call them recursive ones. Recursive neural network. It's the best thing ever. And then a couple of days later, I'm like, I should Google recursive neural network. And then, of course, some people had invented it in the past, but have a more emotional connection now since I had reinvented the wheel a little bit. So this is really just standard, like, taking derivatives again, but there are a couple of subtleties here, so let's walk through those quickly. The main equations that we had derived in their gory details, and you can read up in the lecture notes now too, again we have these deltas, the error messages that come from every layer, and they're basically being passed down the neural network, and we will update the different W matrices here with this outer product of the delta from the previous layer times the activations of the current layer. So those equations will still be the same, but there are a couple of subtleties here. Namely, the following three differences that result from having now the structured object instead of just the same chain that goes, and has different weights at every single layer of the network. So let's walk through slowly through these differences. So the first one is we can actually just sum up all the derivatives at all the nodes, which initially might not be that intuitive, right? Because in theory, this is a function of W, which is a function of W, which is a function of W, and so on. It goes down the tree. So just to give you an intuition here of how this comes about, I basically just wrote down all the gory details for a very, very simple sort of recurrent function. It's the same for recursion. So let's assume here it's just a tree that happens to be a chain. It just goes up and up and up, and there's only one input x. And you could even think through this as just being single numbers. W is just a single number, x is just a single number, and now we just take the derivative with respect to W. Now, we can basically write that out, and assuming W here is the same, we'll apply the chain rule, but now, when you take derivative of a function in multiplication, you now have to take the derivative of both sides if the parameter is inside. And this is really basic algebra. You basically end up with this kind of equation. And now, if we assumed that instead of having the same w here, you actually have a different one. This is w2 and this is w1. So assuming that you had a different w at all the different nodes in the tree, and in this case even simpler than just a simple function, you actually end up with something that looks exactly the same if you in the end just get rid of the indices again. So this is fairly straightforward. You can just write down the derivatives by yourselves, and you'll arrive at basically this kind of property. So really, all we need to do is we go up the tree once, compute all our hidden activations, just like in forward prop with any other neural network, and then we have to go down the tree once. And as we go down, the main subtlety here is now that because we concatenated the two children vectors, we have to somehow split our error messages as we go down. So what do I mean by this? During forward propagation here, the parent is essentially computed using those two child vectors that we had concatenated. And that means that when we now compute our deltas, our error messages, again with the same kinds of equations that we have here, then we will essentially just assume that the delta that comes from that parent and is sent to the two children is just basically a vector that we can now also split the same way we concatenated the children. We can split the error messages from one side to the other. All right, and now the last part is that we have scores at every node, but every node is also part of the score computation of another node, namely the parent nodes, right? So we have here C1 and C2. They have a score, and we want to minimize or maximize that score depending on whether that phrase is in the right or a wrong parse tree. But now their parent will be the left child, in this case, in this kind of visualization here, the left child of yet another combination. And so when we take the derivatives with respect to w here of the parent, that will basically send messages all the way down to the leaf nodes. Every node of the tree sends error messages down all the to all its children in the tree. And so just as before, if we have two different objective functions on top of the same layer, we basically just add the error messages coming from both. So we have here one delta message that comes from the score that we compute, and another delta message that comes from the parent that uses this for computing another score. And you'll actually have to implement this in your last problem set, either this or a convolutional neural network, which we'll go over next week. It's even more complicated, so it's very important to understand this. And I'll give you a little bit of a hint here for the last problem set, largely because I want you to be able to solve the problem set 3 quickly so you can have a really cool epic class project, which is very important, and I think sort of the most interesting lasting sort of output for most of you from this class. So here we basically walk slowly through some Python code for the forward propagation. And just to show you how similar this is to all the other neural networks that you already have with these 3 subtle differences. So you have some kind of recursion that you can implement. There are different ways you can implement recursion in tree structures. But basically, to compute the hidden activation for a specific node, we just basically stack here these two, the left child and the right child, and their hidden activations, which in the beginning, again, could just be word vectors. And then we just basically have a dot product, or multiply this W matrix times this concatenated child vector. So that's fairly straightforward. And then we add the bias term here, and then we apply our element-wise nonlinearity, which in this case could be the ReLU, could be tan H2, and so on. All right, so that's basically the equation of the recursive neural network that I put into a red box. And then we just compute, for instance, a score, or in this case here, a softmax probability. Again, or compute the softmax to get a probability for some kind of class. So we could assume WS, for instance, are here our softmax weights, and you've already implemented this as well. And one interesting side note here, sometimes you will actually run into stability issues when you implement these kinds of models, especially for rectified linear units. Your numbers can get very large. And so this is an interesting sort of trick or hack to prevent overflow in your floating point operations, which is you just subtract the maximum from those numbers. And you should verify that this doesn't really change the probabilities. And then we take the exponent of this, sum over the exponents, and that is basically the probability here for any kind of class, for any kind of node. So what does that mean? We can now basically classify that, you know, the keyboard is a neutral phrase, for instance, in sentiment, and then the buggy keyboard is, you know, a negative phrase, and the buggy keyboard, which I really, really hated when I had to type on it, is now a really, really negative phrase, right? And so you can basically classify all the phrases as you combine different words differently. And this will eventually lead to being able to really classify that this movie didn't care about cleverness, wit, or any other kind of intelligent humor, while having a bunch of phrases that are really positive at the end. And somewhere in the beginning it says it doesn't care about it, and then it becomes negative. So this is basically what this kind of model can do. All right, now comes the interesting part, which is the backprop. So I mentioned there are three different things here. So let's walk through this. Here we have the deltas, which just comes from the softmax. So you've already all derived that in all the gory details, and you've implemented it. So this one should be fairly straightforward of how you compute here your deltas. And again, here you have an interesting, you know, W transpose times delta. That's the first one. Now here comes the interesting subtle notion of having a delta potentially from a parent node as well as from your own prediction. And if you have a parent, which basically every internal tree does, then you will just add your two deltas, the delta that you have from your own softmax or your own inner product for your scoring function, plus the error that comes from your parent. So this is also a recursive kind of function. And then we take our element-wise nonlinearity here, f prime of z, and then it's fairly straightforward. If you are a leaf vector, and this is actually an interesting notion here too, you can train your word vectors as part of the entire recursive neural network model. So in some cases, if your data set is so large for what you actually care about, you don't even have to run word2vec or glove or any other kind of word vector separately. You can just train the word vectors as part of the model. Again, everything is a parameter. The word vectors are a parameter. You just add them. And then as you go through the tree and you send down different error messages in whatever kind of tree, you know, you have delta message coming from here, send down to both of the children, keep sending it down. At the end, they arrive at the word vectors. So why not tell the word vectors, well, if you just changed around a little bit in your vector space, you might actually do a better job in that classification somewhere higher up in the tree. And that pushes the word vectors to be somewhere else. So basically, you can collect here all your derivatives for your word vectors too, just taking the delta that has arrived now at the word vectors. And if you're not a leaf node, if you're not at the very bottom of the tree, but you're somewhere an internal node, then comes in the standard stuff. Here we have the derivative of W will just be delta outer product with the current activation. The current activation in this case was the left child and the right child. So we just concatenate those again and get exactly here the main equation we had derived before. Just an outer product of the delta from the previous layer, outer product with the activation at that current layer. And same with WB here. We had those are just, you add the deltas to the derivative of B. And now you compute the next delta to go down one layer with this equation we had derived, which is just W transposed times your current delta. And now you send those to the two children. And eventually the F prime here again will happen at that node. All right, so this hopefully will help you a lot in problem set 3. But you'll actually have to derive it, and you know I didn't add all the details, and you have to really understand how to send around deltas in a different kind of tree structure. So still a lot of work. So don't wait for too long and thinking this is the entire thing. Yes.
What kind of
This one here is a Hadamard product or an element-wise multiplication. All right, so now we have all our derivatives, and we basically do the standard stuff, which is we take some off-the-shelf optimizer, such as SGD, which we had used. You can also use LBFGS. In most cases, standard optimizers in MATLAB or Python actually have both of these as options. We had also mentioned before to actually use AdaGrad, and this is also very useful here for our model. So we can actually update here again our theta at the next time step of the optimization by dividing over the gradients of all the previous time steps. We mentioned this in one of the tips and tricks in a previous lecture. And it turns out, this is also a subtle difference here that we don't really have to go into too many details with, but because you have here non-continuous objective function, imagine you change the highest scoring tree, and now all of a sudden, because of one little subtle difference in the score at a lower layer in this greedy search procedure, now it's a completely different tree. Now this is a non-continuity, but it turns out you just still take your derivatives and use subgradient. So what this means in practice is we'll basically compute the score here of the correct tree, maximize all those, take derivatives with respect to all the parameters, and increase all those scores. Find here the highest scoring negative tree with our search procedure, the highest scoring incorrect tree, sorry. And then we just minimize all those scores. So there are just two trees at every time step. One tree is the correct one, we maximize its scores. One tree is the highest scoring incorrect one, minimize those. Once they're both exactly the same, well, then those two terms cancel each other out, and you're done with that tree. And you can ignore it and only now try to optimize over trees you haven't yet correctly parsed. All right, so that was the most basic definition of a single matrix recursive neural network. And those actually obtained reasonably good results. And I had a bunch of papers with state-of-the-art results on several different tasks. I'll actually cover some of those in the next lecture. But one interesting problem with them, and this is similar to the recurrent neural networks where we had the same W at every single node too, is that they can't really capture all the complex phenomena of how you should compute and map now all these different phrases into the same vector space. Right? It's a pretty complex procedure. We're asking here a single W, which essentially boils down to just some affine transformation that you add to two child vectors. We ask it to really capture all the complexities of how to create meaning in a language. Right? It's a little too much to ask of a single matrix W. We're essentially asking it to combine different syntactic categories. I have an adjective here and a noun here. And I multiply the first part of my W matrix times the adjective vector, and then the right part times the noun vector. But now, the next layer might have a verb phrase plus now that combined noun phrase. And now I take that same W matrix and multiply it with a verb, and I expect that transformation to also map it into a reasonable part of the vector space. It's a lot to ask of a single model or a single W matrix. And so the idea here is that because we're already in grammar land and we already have these syntactic tree structures, why not use them a little more and essentially condition these composition functions, these neural network layers that have only a single W, and instead untie the weights, relax the assumption. This comes back to a question that was asked before, which is, should we really use the same W here at every single node of the tree? And what we could do instead is actually condition these composition functions on what kinds of syntactic categories they're actually combining. And this is an interesting notion here, so let's walk through an example. So here, this is the standard recursive neural network where we use the same W here at every single node in the tree. And now let's assume we have actually some knowledge about what these word vectors are. And this knowledge comes in the form of discrete categories. So let's say A, B, and C here, capital letters are actual discrete categories. So maybe this is, I, so this is a personal pronoun, and we know this vector here is a personal pronoun. Like is a verb, and cats is a noun. And so C here is this is a noun phrase. B here is this is a verb. And now we'll actually use a W matrix here that we select different W matrices. We have a large set of them, usually they're around 80 or so, and depending on what syntactic categories you have, you use a different W. So here we have the first W that combines syntactic categories where the left child is of the syntactic category B and the right child is of syntactic category C. Yes?
How do you get these syntactic categories?
Right. So how do you get the syntactic categories? Basically, you use a very simple model that is not very accurate, but basically just looks at the summary statistics of your corpus, your training corpus. You know what the right trees are, right? The linguists, again, had sat down, created, for instance, Penn Tree Bank. And in Penn Tree Bank, you can know, all right, these kinds of things only ever combine this kind of way. And just taking those counts basically boils down to probabilistic context-free grammar. And we can't really go into the details in this class, but it's a very simple generative model of parse trees. And in its most simple form, it's very fast, but it's not very accurate. But it turns out it's good enough to give us a bunch of candidates which we can then go over. And it's also good enough to help us condition and get syntactic categories. Yes?
So since you have probabilities for each syntactic category, could you weight each matrix by the corresponding probability?
We will actually compute this final score as a sum of the recursive neural network score as well as log likelihood from the PCFG, but we're not going to weight them. But we will get some weighting coming from now having different composition matrices W, and I'll show you in a second what these look like. Yes?
Why don't we use a more complicated function like a deep or network as each one?
That's a good question. I think you actually have the option here to also use a deeper network. You could also just classify each of these vectors here in a separate, with a separate neural network and say, all right, I classify this as a verb phrase, I classify this as a noun phrase, and then I condition my my composition function based on these classification problems. It's actually also a reasonable option. All right, so basically for, yes?
Is determining the category P of the combination, the capital P of the combination, something that's done using the neural network, or is that something that's deterministic?
It's a great question. So we will actually, in the simplest case, just assume, let's say we have a model that gives us, for each sentence, 200 candidates where we know the syntactic categories of every single phrase and word. And this, in our case, will be a very simple, fast PCFG model. Don't worry if you don't really understand PCFGs. If you've taken 224, good for you. If not, let's just assume you have some oracle that gives you, for each sentence, 200 or so candidates of what could the right structure be. And ideally, you know, in over 95% of the cases, one of those 200 is actually the right one. It just turns out the model that gives them to you doesn't actually know which one is the right one. And so it helps us basically to prune very unlikely candidates, which is just a speed hack. We could use a neural network, but then you have lots of matrix multiplications inside to compute all these potential candidates. And this one helps you. And it also provides you some coarse syntactic categories of the children. And so we'll call this full model here a compositional vector grammar. It basically combines a simple model like a PCFG with a more complex recursive neural network. There's been a bunch of work on these, and in most cases it's quite different. They assume fixed tree structures. They didn't actually do mixed margin learning. They didn't actually use a large trees and long sentences and so on. There's also been a lot of work in parsing where people have basically taken the manual feature engineering approach and tried to improve the original simple PCFG where you just say this is a noun phrase. And without going into too many details here, you can basically look at all the errors you're making and try to describe each of the categories with some richer but still discrete representation. So in some ways, and sort of historically, this kind of model extends all these other ideas from taking counts over discrete kinds of information to just representing everything as a non-discrete, as a continuous vector representation. So the numbers here are in some ways not that interesting. There's lots of work on this task. A lot of researchers in natural language processing care about parsing. And so there's been lots of different work here. What's interesting here is if we have the same weight matrix W at every node of the tree, we actually don't get a very competitive parser. But once we allow the syntactic untying, having different W matrices, we actually get a very good parser. There's still other ones that take into consideration even more external data, but they're much, much slower at both training and testing than this one. And the way we measure this here is again with F1, where we have precision and recall over the various nodes in the tree. What's more interesting is that linguists had a certain notion of soft head words. In fact, one of the baseline models here from Collins tries to lexicalize these parsing decisions and say, well, this is a noun phrase with a cat inside, for instance. Or in this verb phrase here, maybe the verb matters more than the noun, because in the end, the action sort of matters more than maybe the things that depend on the action. What's cool is this model actually learned what linguists had themselves sort of come up with by trying to analyze grammatical structure in language. So it, for instance, learned that when I combine a determiner like the or a with a noun phrase like cat or church or windows, that the noun phrase actually matters more. So what do we see here? This is essentially exactly this kind of matrix. The left block of is the matrix that is multiplied with the left vector. The right block is the block that is multiplied with the right child of that phrase. And now here we basically just visualize how large our elements are. And I had brought up in a previous lecture that there's this sort of this hack of initializing these matrices with identity matrices, and that's exactly what we did here too. We start by having 2 block identity matrices. So the default in the very beginning of the model, if you don't know anything, is actually just to average the 2. You start here with 1/2 times these 2 identity matrices. So you have here 1/2 times an identity matrix, basically just comes down to 1/2 C plus C1 plus 1/2 of C2. So, and then, you know, of course you apply the nonlinearity. But in general, when you start out with, that's what you get. And then slowly but surely the model pushes itself to basically start to ignore more and more with its the cat or a cat or this cat or that cat, literally, and just realize, okay, the most important thing here for the semantics of the resulting phrase is that it's a cat, not that it's the or this or a. And that's really neat, right? The model here learned something that linguists had also come up with through many years of research, but the model learned it just from looking at lots of data. What's more interesting is we can actually now look at what these word vectors and phrase vectors are capturing. So we can look at nearest neighbors in the phrase vector space. And just like with word vectors, the word vector spaces basically captured syntactic and semantic information. Nouns were closer to other nouns. And then once you zoom in, the semantically similar nouns are closer to other semantically similar nouns. The same thing is kind of true for phrases. It's of course much harder because in general, for most sentences in most reasonably sized corpora, there might not be that many other sentences that are very, very similar to that. Sentences is a much more complex space. And a lot of NLP researchers had actually initially argued that it's almost ridiculous to squeeze a variable length sentence structure into a fixed vector representation. I think now it's becoming more and more common, and with the results from machine translation that we covered in the last week's lecture, we actually see that, well, it is a reasonable enough representation to really capture a lot of subtle information. So here, what we did is we basically took the top vector of one of these sentences, and we mapped a bunch of different sentences, in this case from the Penn tree bank, into this vector space. And then we pick one sentence, and then we look at the nearest neighbors of that sentence in the resulting vector space. And for the sentence, all the figures are adjusted for seasonal variations. The closest sentence to that one is all the numbers are adjusted for seasonal fluctuations. So here, it basically just learned, well, if I have 2 similar word vectors, variations and fluctuations, and figures and numbers, but the rest of the tree structure is the same, well, that still keeps them the same. So that's maybe not that impressive, right? But the next one is interesting. All the figures are adjusted to remove usual seasonal patterns. So here it actually learned that to remove usual seasonal patterns is kind of similar to seasonal fluctuations, or adjusting for those. And so it actually had some sort of invariance to adjusting here a whole verb phrase versus adjusting just directly this noun phrase. And Nightritter, a bunch of organizations, wouldn't comment on the offer. The model learned that that's somewhat similar to Hoshko declining to say what country placed the order, or Coastal wouldn't disclose the terms. So it learned here that, you know, to wouldn't comment and decline to say and wouldn't disclose are similar kinds of things that companies would do. And personally, I was very excited when I saw these kinds of results in 2010, and that was one of the reasons I sort of went into, you know, deeper and deeper into deep learning. Because it kind of learned some interesting patterns that we didn't explicitly tell the model to try to capture. It basically was also the first step into thinking about applying these models to paraphrase detection or understanding semantic similarity between different sentences. And for those of you who think about, you know, summarization, this is also an important kind of result for sort of sentence summarization, not including the same sentences multiple times. Another interesting one was exactly this example that I brought up from the beginning with the entity, the PP attachment ambiguity. So the prepositional phrases and where they should attach. Should they attach to the nouns or the verbs? So here the question is, can we transfer semantic information from a single related example? So here the idea is we add 2 training sentences and then we test on these 2 test sentences. And all these 4 sentences are actually incorrectly parsed when you take any or most of the standard parsers, because they were usually trained on a Penn tree bank, which comes from the Wall Street Journal. And the Wall Street Journal just doesn't talk much about eating spaghetti. So they're almost all incorrect, or all for most parsers. And then we basically add these. And now, because we use word vectors to make these decisions, we don't need to see exactly spoon and meat at training time, because at test time, because at training time we saw fork. And from our word vectors, we know that fork and spoon are actually 2 similar kinds of things. They have similar vector representations. So the hope here is, because we don't think of these as discrete entities and we just keep counts in a probabilistic model and we keep counts for fork, and now, well, you know, if you've never seen spoon before, your counts for fork don't really help you. If, however, you learned a neural network model that takes as input something that looks like a vector in this area of the space, and you find something else that is in that similar space, such as, you know, fork and spoon having close word vectors, then there's some chance that this will happen. And that's exactly what did happen, which is we had here the original Stanford factored parser, which didn't get the PP attachments correct, and the compositional vector grammar I described before correctly put the prepositional phrase here with a spoon to the verb phrase and with meat to the spaghetti. Yes? Sorry, say again? How were the children discovered?
So I can see on the bottom left, looking at the parse which has the verb phrase which has 3 children. I'm curious because you can explain sort of like the recursive structure of the neural network as having these 2 stacked W matrices. How you can assign 3 children.
Oh, this one right here. So the question is, how did we actually get from the binary tree structures that I described to ternary ones? It turns out any grammar in Chomsky normal form can actually be binarized, and then you can have a deterministic procedure to get back, to basically map between a binarized version and one that isn't binarized, and still recover the exact same grammar. And so this is basically a deterministic sort of post-processing step to then create ternary structures. You could also, in the greedy search procedure, actually have a W that just has 3 blocks, W1, W2, and W3, and you just multiply it with 3 word vectors and compute, you know, again, a parent vector P for that. But it just turns out that if you try to use CKY-like chart parsing, then that blows up your complexity even more. So you'd rather just do it as a post-processing step. Don't worry if you didn't understand all the things I just said. Okay, so I showed you in the code that we can use these parent vectors also to compute any kind of class, right? We can predict sentiment for every phrase. We can predict the syntactic categories. Lots of different things we can predict. And we will do that with a softmax classifier at every node. And again, we train it similarly to before. And in the case of the actual parser, we can actually train this by having the scores, and we just add the two errors. The max margin error, we add the cross-entropy error, and we just take derivatives with respect to both. Same way we did before. So now let's think about scene parsing. It's actually, in some ways, and this is kind of a fun side note for the last 3 minutes, that shows you that once you are really good at deep learning for natural language processing, you really now have a tool in your bag that lets you do almost anything that is related to data. Because almost every data can be represented as some kind of vector, and you can use these kinds of techniques for lots of other things. So last little 3-minute side note here on computer vision, where you could kind of assume that even in scene images, you have a similar principle of compositionality going on, where you can define the meaning of the scene as also a function of the smaller regions. You know, there's a bush, there's some people, there's a roof, there are a bunch of different objects here, or parts of a larger structure. You have a tree. Now, the single parts of the structure compose to form a building, and then all these various objects interact in certain ways. And it turns out that I don't need to actually describe to you in many details how you would learn how to combine little regions, because it's the exact same neural network that we just described for sentence parsing. The main difference here is, instead of starting with word vectors for words, we actually start with feature vectors for little regions and images. And there's some computer vision technology in how to actually compute those and program that. But let's assume we have a vector representation that captures features of small image regions. Well, now we use that exact same neural network. We have a bunch of neighbors. Now it's not just the left word and the right word, but all the regions that are neighboring a certain other region in image. We can compute scores for whether we should combine them or not. We have some training data for that. That says, this part, all these different regions are actually part of the same, building or street or group of people or tree or whatever. And then we increase scores for things we want to combine. We decrease scores for things we don't want to combine. And that way we can build these whole structures. And this kind of model actually, back in 2011, was a state-of-the-art model. Since then, actually, people have come up with even better models, all of which I think are also deep learning based. But here you can basically see, what kinds of things it labels as street or trees or buildings and so on. And so yeah, hopefully that shows you that really the kinds of tools you learn here, and we've already seen this for some class projects. Some of you are using these tools to understand genetic language instead of natural language. But really, it's a very general set of tools that you're learning here. All right, and that's it for today.